I'm going to start by talking about the Galaxy Halo connection. Sorry, the AGORA project update, I mean. I want to emphasize that Ji-Hun Kim and Santi Roca Fabrega, who are here, are the real leaders in practice of the AGORA project. And they're going to be leading the discussion tomorrow. So this is the history. We have an online workspace that is constantly being updated. We've published 2 articles. We have 2 more articles in progress now. We've had many workshops and many telecons, continuing up to the present. The first paper compared simulations with 9 different codes, just dissipationless simulations. And although they look sort of similar, if you look in detail, they're somewhat different. The second paper was an isolated galaxy, supposed to be a Milky Way type galaxy at redshift 1 with about twice the amount of gas. And again, there are 9 different codes, 4 adaptive mesh refinement codes, 5 smooth particle hydro codes, and they look a little different, but when you do detailed comparisons, surface density profile, rotation velocity profile, velocity dispersion profile, Kennecott-Schmidt relation, these are all, each one of these graphs has all 9 codes. And they're remarkably similar. Now, how did that happen? Well, it turned out that there were a number of errors that were found in this detailed comparison and fixed. Runtime parameters that were set to be similar turned out to be rather different in practice. And so we had a lot of learning as to what really controls things like the star formation rate. And there were actually numerical errors in some of the codes that were caught through this detailed comparison. So the idea is that we compare simulations with and without feedback or with different feedback recipes with themselves, with each other, and with observations. And that should increase the predictive power of simulations. So the current projects are focusing on the circumgalactic medium in a Milky Way mass galaxy and the clumps, exactly what Yi-Ching Kuo was just talking about. This requires higher resolution, so first we're focusing on this. And the names in blue are the leaders, as of now basically, of the code groups. And there are 6 code groups that are very actively working, and a couple more of it may join. And we've had 12 telecons and workshops, and still counting. And then there are telecons every few weeks. So there are 9 people who are going to be attending in person the meeting tomorrow, which is over in the ISB building, where many of the physicists and astronomers have their offices. And we'll also have about the same number of remote participants. So small errors in Grackle cooling have been found and fixed. UV background and self-shielding have been found, errors have been found and corrected. There's a particular error in the Grackle cooling code that's now been solved. So if any of you use Grackle, update to the latest version, 3.1.1. As I mentioned, there's all these online meetings, roughly monthly or even more recent. We're calibrating all of the models to have roughly the same stellar mass at redshift 4. And we expect that this is going to be a useful effort, not just for ourselves, but for the whole community. So these are examples of temperature density, phase diagram plots. These are a couple time steps of 5 different codes. And now, since I really don't have much to say about the work, I'm going to tell you something completely different, but in the spirit of some of the other talks today, which has to do with the Galaxy Halo connection. There's this recent review, but I wanted to tell you both about some old stuff and then about some new stuff. So the old thing I wanted to mention has to do with perhaps the earliest mention of what we now call assembly bias in the literature. Maybe somebody can tell me, oh no, here it is even earlier. But this was in the first of the 2 dissertation papers by James Bullock, working with me and Avishai Deckel especially. And in the conclusions of that paper, we said high concentration halos collapse earlier than low concentration halos. That's what we learned in that paper. And a natural association is then that high concentration halos host old red galaxies, and lower concentration halos, which are more recently forming ones, host young blue galaxies. Furthermore, halos in low-density environments tend to be less concentrated. Halos in high-density environments more concentrated. And so that would suggest that the clusters in very dense environments are the ones that host early-type galaxies, which, of course, are all trends that we now know. This has been rediscovered many times. But as far as I know, it was first in this article. And actually, Sandy likes to emphasize that it was even prefigured in our cold dark matter article back in 1984. OK, so now for some new stuff. I'm not going to have time to talk about this fact that the dispersion in the mass accretion rates of halos seems to be a plausible explanation for the exact same dispersion that's now well known in the main sequence, namely about 0.3 dex, factor of 2. So I'm going to skip that and go on to talk about, very briefly, the semi-analytic model, semi-empirical model, rather, no physics, just fitting all the data, that Aldo led. And there are two key points that I wanted to emphasize that the model naturally fits in the data and shows you how it's connected to other things. The radius, that's the effective radius, the half-light radius, grows slowly, roughly as the stellar mass to the 1/3 power in star-forming galaxies, but switches over and grows much more rapidly after quenching, and that this is due to minor merging. And also, the central surface brightness in the inner kiloparsec, sigma 1, like is what Sandy likes to call it, grows until quenching, and it's higher in higher mass galaxies, and the quenching occurs at higher redshifts. So there's a quenching downsizing phenomenon. So the way this kind of work works, and there are three recent semi-empirical models, Ben Moster's model and Peter Baruzzi's model, which he calls the universe machine. And what everybody has to do is take a given set of papers on stellar masses and star formation rates, and then turn them into something that can be compared by correcting for different assumptions on initial mass function, cosmology, et cetera. So this explains in the table and in the text of the paper in much detail exactly what was done for each one of these different. And then if you do that, it turns out that the star formation rates versus mass and redshift actually agree remarkably well. Although if you read the papers without making these corrections, it looks like they don't agree. Once they agree, then you can fill out diagrams like star formation rate versus mass, stellar mass, virial mass, and redshift, and get a stellar mass halo mass relation. Now we're adding two things in this model to the earlier sham or ham models. We're taking into account the radius of blue galaxies versus red galaxies, and we're also taking into account the merging rates from the halos. And that allows this model, this fit to the data basically, to show that when galaxies quench, this is the quenching band, so this is as the mass increases, galaxies are on the star-forming trajectory, then they quench, and then the radius increases very rapidly with mass, slowly here, very rapidly there, and that's accompanied by a change from being dominated by major mergers to minor mergers. Minor merger rate goes up, major merger rate goes down. And this is what's showing this downsizing of the quenching phenomenon. So this is the inner kiloparsec. Now the thing I want to emphasize is this is done in a really, really simple way. And yet this phenomenon, which was shown much more carefully in detailed studies, just leaps out that after galaxies quench, the central stellar density basically plateaus, and that this happens earlier for higher mass halos. Okay, I only have time to sort of advertise these results, and I want to tell you a bunch of them. So in this project, led by my now finished graduate student, Christoph Lee, what we did was to measure the mass in 1 billion voxels at a number of redshifts in the Bolshoi-Planck simulation, and then smooth on scales of 0.5 megaparsec, 1 megaparsec, 2, 4, 8, and 16. Every place in the box, we then knew what the density was on all those scales, and then we tagged every halo with that density, and then we looked for every cross-correlation. And then in this paper, we reported the ones that seemed particularly interesting. And so look at this. We look at many things. I'm just going to point to one that's kind of interesting. So these are Milky Way mass halos, lower mass halos, 0.75 dex lower, higher mass halos, groups, small groups, big groups. But notice that in every case, once you get to the average density of the universe, that's here, this is higher density, lower density, the spin parameter plunges by 30% or so. So halos in low density environments today have significantly lower spin parameter. Why is that? Well, spin parameter is due in principle to the interaction between nearby halos. They torque each other up. And in halos in low density environments today have always been low density environments. And so they've had fewer halos to torque them up. And that's not just a speculation. We verified it. We actually measured what the tidal torques were on the halos, and we showed that that's exactly what's going on. So it's not surprising, but it's interesting. Among other things, this suggests that if it was the spin parameter of the halo that determined the size of galaxies, galaxies of the same stellar mass, same halo mass anyway, in low density environments would be smaller because they have lower spin parameters. But they're not. So this is another argument, in addition to the one that Fangzhu Zhang has discussed and others have seen, that in simulations there's simply no correlation between the spin parameter of the halo and the size of the resulting galaxy. This is yet another reason that, and there's lots of other interesting stuff here. Okay, but I don't have time to go into it. I'm basically advertising this paper that was published 2017. Now, a second issue that you can look at is, if you have halos at the same density, say on a 2 megaparsec scale, in the edge of a void or a wall or a filament and a node, is it the location in the cosmic web that determines the properties of the halo, any properties, or is it the density? And the answer is, except for orientation, it's the density. Otherwise, the halo location is essentially irrelevant. And this shows that. So this is the same three things I showed you before: concentration, spin parameter, and accretion rate. And here we're color coding the different environments, the different web environments, as classified by Miguel, Eric, and Calvo. And the only difference that you can see in all of these is a slight difference in walls versus other environments in the spin parameter. But that's the only difference that we could find. So in other words, it's the density that controls. The one thing where the environment, the halo environment, the cosmic web environment matters is the orientation of the halos. For example, standard result, halos and walls tend to have their angular momentum pointing in the plane of the wall. We checked. We found exactly the same thing that everybody else has found. Yep, that's true. Okay, moving on quickly. Halo mass loss. So it turns out that about 20% of halos at redshift 0 in the Bolshoi-Planck simulation have lost at least 5% and often 10 or 15% of their mass compared to their highest mass at some earlier stage in the simulation. So what's the cause? So we looked at lots and lots of halos, and the blue dash curves are major mergers, and this heavy red thing is a time when the halo is being tidally truncated. And so what you see is that in mergers, the mass goes up, and then it comes down. Mass goes up, and then it comes down. The scale radius jumps way up, because after all, there's two centers in the middle of the merger. And then it comes down. That means that the concentration is going to go in the opposite direction. It's going to go down and then go back up. The spin parameter goes up and then comes down. That's because the high angular momentum material tends to move to the outer part and even beyond the virial radius of the halo as the halo relaxes. There's the relaxation. This is the kinetic to potential energy in a major merger that goes up and then it comes back down. So to summarize, concentration, if a halo loses a little bit of mass, goes down, and if it loses a lot of mass, which only happens in stripping, it goes way up. Spin parameter works the other way. Well, many, many more details of what happens to halos as a result of both merging and the relaxation after merging and during tidal stripping are discussed in this paper. Does the stellar mass halo mass relation or the galaxy luminosity halo mass relation, these standard relations, do they depend on density? I've just told you halo properties do depend on density. What about abundance matching? Good news, this was a project led by an undergraduate, Radir Dragomir and Aldo. The good news is no. Density is essentially irrelevant. What we did was to make a mock Sloan survey, populated with galaxies, assuming stellar mass, halo mass doesn't depend on density. And the only exceptions that we found were basically in U-band, where recent star formation has a big effect. And so the brightest galaxies are over-predicted, and the faintest galaxies are under-predicted. Sorry, I said it right. The high-density regions we're over-predicting, and then the low-density regions we're under-predicting. But aside from that, in every other band, and for the stellar mass, except for this low-density region at the highest star formation, highest stellar masses, there's really no dependence on density. So, and then finally, I wanted to just mention that there's a whole bunch of things that we've discovered about the nature of galaxies that are only about 10 to the 9.5 to 10 to the 10 solar masses or less at redshifts of 1 and above. And Arjen van der Velde led the Candles paper in 2014, the second of the papers he led in 2014, that showed that the axis ratio distribution of these galaxies is such that there's a preponderance of low axis ratio. That is, short axis over long axis tends to be low. And that means they can't be spheroids, because by definition a spheroid is more or less spherical no matter how you look at it. That would have a high axis ratio. And they can't be disks, at least not very many of them, because you're going to see disks in every orientation. If you see disks face on, they're going to tend to have an axis ratio near 1. If the axis ratios are low, they can't be disks. They have to be primarily little pickle-shaped things. Hao and Zhang led a study that we just published that showed, in a more detailed analysis, where we took into account, as Sandy emphasized we should, the size of the galaxies, that this is basically true, but that the smaller size galaxies, that is where R effective is less than about 3 kpc, those galaxies are actually primarily spheroidal. But the bigger galaxies are primarily, at these low masses and high redshifts, are primarily pickle-shaped. In this paper led by Daniel Severino with Abishai and me, we showed that we saw exactly the same thing happening in the Vela simulations. and that the key thing was whether the center of the galaxy is dominated by dark matter or not. When the center of the galaxy is dark matter dominated, the galaxies tend to be very prolate, aligned very well with the long axis of the prolate halos. When a compaction occurs, that is a rush of gas into the center, big central starburst, the galaxies then became round, and then often a disk formed around that. And the details of that were discussed in this paper led by Tomasetti, then a postdoc with Abishai. And that then suggests, since we found in that paper that the halos were oriented along their filaments, that suggests that we should look for the nearby galaxies, especially these low mass galaxies that are mostly pickle-shaped, to actually be aligned. And Viraj Panja led a project that the paper was just accepted, and it's on the archive. And we didn't see that alignment. I'm just finishing. And so the puzzle is, why didn't we see the alignment? And we're pretty sure the reason is that we have almost no spectroscopic redshifts for those galaxies. They're low mass. Well, there's various reasons we think but only about 5% of those galaxies have spectroscopic redshifts, and that's not enough to get enough close pairs that we can actually measure the alignment. So an interesting project is how many more would we need, and what's a good opportunity to get them? Okay, well, to summarize, the AGORA project is collaborative, and we're trying to get reproducible and understandable simulations. We want to increase the predictive power of the simulations, and there's a great opportunity for people to get involved. And again, this is my advertisement of a lot of recent results that we're still learning by analyzing dark matter halos.
Questions?
So I understood that in some conditions, the concentration and spin parameter of a given halo evolve in different directions. So I didn't understand the answer to a simpler question. So at fixed halo mass and redshift, are the concentration and spin parameter anticorrelated with each other or not?
I didn't look at that question of spin parameter versus halo concentration correlation. I don't know.
All right. Thank you.
We could easily answer that. Maybe Aldo knows the answer.
No, we haven't looked into that.
But I should tell you, the Rockstar and consistent trees analyses of Bolshoi Planck and multi-dark Planck, small multi-dark, big multi-dark, middle multi, are all publicly available. And all that information is in those catalogs, and anybody who wants to can easily check that.
Yeah, including the density information. You can get those from the public available catalogs. So, another question? If not, well, let's
time for lunch.
Yes, you can ask Job on lunch.